welcome back. This is the final module from this video on for the next few videos. This is the final module of the deep learning series that we have been doing so far. Next week we will do some conventional machine learning techniques that were non deep learning techniques in the next week. So, this final module is for what is called recurrent neural networks. So far you have seen a couple of main techniques for deep learning. One is for artificial neural networks. Very heuristically speaking, this is good whenever we are dealing with pure numerical or number like data. Okay. This is in the context of, again I am saying this in the context simply of engineering or science problems. For example, if you want you have temperature and pressure somewhere and you want the density for a specific application, maybe you could, if you think that these are the only two variables in play, you could use artificial neural networks to predict something of that sort. Once again in week 10 or so we will actually see a whole variety of applications where this distinction will become clear. Okay. So, that is for artificial neural networks, and you also saw this, of course, is AlexNet. We also saw convolutional neural networks, CNNs. These are primarily for image like data. Okay. So, when you have data in the form of pictures, then we use CNNs. Once again we will see applications of this. Dr. Ganapathy has shown you a few applications already in medical image analysis. We will show you a few more in proper engineering problems or science problems in a couple of weeks from now. Okay. So, we also saw that CNNs are essentially a special case of artificial neural networks. Now, you have a third class of data or third class of problems, which is what RNNs deal best with. Okay. Now, ANNs and CNNs have a couple of lacunae, they have a few problems. The problem is that your inputs are of fixed size. Okay. So, for example, if I use temperature, pressure, that is what I am forced to use each time. Now, there is a subtle point here in what fixed size means. We will come to that when we come to RNNs, both in this video and in the next. Okay. Now, more importantly, you need that the whole input be available simultaneously. Okay. So, you have to give the input, for example, the image here has to be given one shot, you can't later decide to give another image. So, that image is given and you get an output. Okay. Now, compare that with something like, let us say, making closed captioning for what I am speaking. Okay. So, you do not have typically, and suppose you have an online translator, that is, as I am speaking somebody is writing down what I am speaking, or Alexa interprets your input as you speak, okay, or your car does things as you speak. So, something of that sort requires sequential processing. So, some of the typical problems that are used in RNNs are recurrent neural networks, okay, involve typically speech processing. Okay. So, like I said, Amazon Echo etc. will be using an RNN somewhere within there. Okay. So, speech recognition will be there. Language translation, for example, Google Translate. Okay. So, that uses some form of RNNs. Okay. Video analysis etc. all these things where sequence matters, that kind of problem typically involves recurrent neural networks. So, the key ideas which are important in deciding whether RNN is an appropriate model to use or not is a variable sized input, okay, and sequential information. Even if it is not quite clear what variable sized input is, it will become clear by the end of this video and the next video, okay. But sequential information is something that is quite important. Now, sequential information typically means, in engineering speak, time like or time series like data. Now, of course, RNNs are also used, and currently the most popular use of RNNs is in language, okay, or in what is called natural language processing. This involves series of words, like I said, translating from one language to the other. Google has Google Translate, all those applications use RNNs because words come and they are in a sequence. Also sentences are not necessarily of a fixed size. Okay, you can have a short sentence, you can have a long sentence, and you know that kind of you have to translate sentence by sentence. Now these we will not be discussing really language applications, that is not the purpose of this course. We are only going to basically discuss overall ideas behind RNN, some of the architectures, just like in CNN you saw a few architectures, we will be discussing a few architectures within RNNs also, and we will also show you what kind of tweaks you require for putting it into engineering problems, specifically actually in week 10, but I will show you one example this week also. Andre Karpathy has written a very nice blog post. Also there is a course called CS231N which is called Convolutional Neural Networks, but it does discuss basics of RNNs as well as CNNs. So this idea is actually borrowed from Andre Karpathy's a very nice blog post which we will post on our website also. So this is called the unreasonable effectiveness of RNNs. So I would recommend that all of you take a look at it. It has some very nice language examples. We will not be using too many language examples, at least within this course. So, but if you are interested, you can take a look at that. He also has posted his own Python code on GitHub there. Okay, so this is not very standard classification, but Karpathy has classified the types of RNN architectures that you will see into 5. So this is called one to one, this is called one to many, this is many to one, and these two are many to many. Okay, once again this is not really classification that is there in the literature, but I think it is a great sort of way of classifying it for introductory purposes. So we will look at that. So let us look at some examples of where RNNs are used, once again very notionally, and we will go into depth a little bit later in the next few videos. Okay. So here this red block here simply is our usual input, let us call it x. This green block here in the middle is our hidden layer, and the blue block here is our output layer. Okay. So as usual, input, hidden, output. Now this one to one classification is basically our usual ANN. You can even think of it as a CNN in case there is only one or many. You can even think of this H as if it is many layers, but let us assume it is one. So it is not a particularly good CNN, but let us assume this is simply a ANN with one single hidden layer and you have an output layer. So whether it is RNN, ANN or CNN, as long as there is only one, okay, you basically can say that all three are equivalent. So this would be what would be called a vanilla RNN or a simple RNN structure. Okay. So up until so far there is nothing impressive about an RNN. So let me show some results. I must point out that I got these results off the web a little while back. I have kind of forgotten where I got them from. So if somebody can point it out, I will actually put up an explicit acknowledgement on the website. So please let me know. So this one is a one to many classification, and this is where RNNs kind of start differing from ANNs and CNNs. So what is happening here? You have a single input and you have got a bunch of outputs. Okay. Now what is that like? This is as if you have a single image which is the input to your problem, and what the output here is a bunch of words. Okay. Now how does this magic happen? Again we will see a little bit of it in the next few videos, but the basic idea is very simple. As usual, it is just a mapping. You somehow have to map one input here to a bunch of outputs. Now what each of these outputs means we will see shortly. Okay. But let us assume this corresponds to word 1, word 2, word 3. Okay. Now you can see that just by seeing an image there has been a fantastic output here saying a dog is running in the grass with a frisbee. Okay, so that is remarkable. Of course, it is not simply a one to many RNN as I have shown here, there are many other tricks going on and that is well beyond the content of this course to go into every detail, but hopefully at the end of this course you will be able to read papers like this, image captioning papers, and be able to figure out what is actually going on. Okay. And similarly, there is a question asked based on a figure and you are supposed to figure out which of these choices is correct, and the fact that this picture was taken during a wedding. As you can probably figure out by what we have talked about so far, a lot of it depends on how you train. Okay. So, training is a very important part of how this kind of output can be gained. But a simple this was just shown just to show a simple example that there could be one input and many outputs. Okay. Then you could have a bunch of inputs, the opposite case, which is many to one. You have a whole bunch of inputs and one single output. What would that be like? That is like giving a sequence of words and trying to find out, this is called sentiment analysis. An example of this is just trying to find out whether this is positive or negative. So, if you read somebody's feedback report and somebody has written it in words and you simply want to figure out is this a positive feedback or is this a negative feedback. Some student at IIT Madras actually did a nice work of analyzing Twitter feeds of many companies, stocks, and trying to figure out whether the sentiment, market sentiment for this was positive or negative. This can be done automatically. Once again, if you use an RNN structure for this, it would be a many to one structure, a whole bunch of words with one output, is this positive or negative. You can do several things with this. The third kind of task would be many to many, and this itself splits into two. Okay. A many to many is such that you have a whole bunch of inputs, you have lots of outputs, but the outputs need not come simultaneously with the inputs. Further, the outputs need not have the same size as the input. Okay. For example, if I translate one language to the other, okay, suppose whatever I am speaking is changed into Tamil, the number of words in my English speech need not be the same as the number of words in my Tamil speech. Okay. So, similarly, you can see Google Translate also works, it is not as if it is a one to one map, it is just that some bunch of words was given and after that some other bunch of words comes out as output, and that would be a language translation task. Similarly, speech recognition, why would that be a many to many task? One, of course, when I speak there is this length of my audio signal, the length of my audio signal need not be the same as the length of the number of words that I am using. Okay. So, this is also a many to many task where the input size is not the same as output size, need not be the same, okay, not generally be the same as the output size. Now, there is a final many to many task, and in fact, we will show you an example of this in the very next video. The many to many task here is where input size is the same as the output size. Okay. So, for example, a frame by frame classification of a video, and I will show you another example next time, which would be trying to figure out what a person is doing based on sensor data on that person, and you want to know what that person is doing every second. So, whatever input you have a corresponding output, at least you have equal number of inputs and outputs in such cases. So, all these are, I would say, traditional examples of what RNNs are used for. Okay. Our interest, of course, is to try and find out engineering examples, but before that let me just show you the rough structure of an RNN. I just showed it as a box. So, let us get into slightly more detail within this video about what is done. Okay. So, the general idea is variably sized sequential data. Okay. What does variably sized mean? Okay. So, variably sized means that even though number of features is fixed, the size of data is not. Okay. So, this might be slightly confusing to you, it is best explained in terms of a couple of examples. So, we will see that later on, just keep this at the back of your mind. Okay, what does variable size mean, and we will see this both in this video as well as in the next video. Okay. Now, what is the basic idea of a RNN? Same as most ANNs, which is you combine an input vector, okay, you get an input vector and you get an output vector, except in this case you have a slightly different architecture. It works like this. You will see this in the pictures that I have drawn so far. You have one input vector here, you have an output vector, a hidden vector here, and we will have another hidden vector here. So on and so forth. Now, this hidden vector, let us say if I take h2, is a function of two things. It is a function of x2, it is also a function of h1, okay. And you will see in the next video how this can be tremendously useful. In fact, later on in this video itself I will talk about this. Okay. So, this is a function of two variables, x2 as well as h1. So, usually this many people find this very confusing. This is a usual representation x RNN and it loops into itself. You will understand why this is so very shortly. Okay. But most of us, including Professor Andrew Ng, do not prefer this kind of picture. We prefer this picture which is called an unrolled RNN. Okay. So, I would recommend that at least for thinking purposes you think about in this way, but if somebody uses this you should be able to understand it. So, I will show this a little bit more in this video. Okay. So, remember this, you have one hidden vector, it depends on the previous hidden vector as well as the input vector at that particular time. This axis, even though sometimes I will abuse notation and call this number of layers, it is actually a stand-in for time. So, as I keep on moving here in all these pictures, you can think about it as if you are moving in time. Okay. 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 So, here is some theoretical detail, I will discuss this and then I will come back to how this function works. Okay. So, these are, if somebody is from a computer science background, theoretically remember that we had the universal approximation theorem for artificial neural networks that said that I can take a large enough ANN which will approximate any function that I would like. Okay. Now, RNNs have a similar property in that they can simulate or they can come close to approximating any program. Okay. So, any computer program can be sort of simulated, because remember, for a computer program all your inputs might not be available simultaneously. Okay. So, you might say something now or you might give some data now, and after some time the computer asks something else and you give new data at each point. Okay. So, RNNs are supposed to simulate a generic function which can move and it can take inputs at varying time instants. Okay. So, that is the speciality of RNNs. So, once again theoretically we know that RNNs are what are called Turing complete, that is they can simulate any program. Okay. After this brief note, just sort of a theoretical note, we will move on to a practical thing. Okay. So, let us come here, let us come to the structure of an RNN. Okay. Let us take a simple example and explain it via that. Okay, so, remember the structure. Okay. So, let me show you a problem and we will come back to this picture. Okay. So, let us say I want to find out today's temperature, I go on Google and indeed Google gives me today's temperature or yesterday's temperature as it might be. Okay. Now, not only does it give that, it gives you a few other things. It gives you tomorrow, day after, the day after that, etc., etc. Now, how does it do it? Now, of course, they are not using RNNs here, I want to be very clear, even though I am using weather prediction as an example or temperature prediction as an example, It is a very simple example with which we can kind of understand RNN ideas, but I do not think that Google is actually using any such thing. It is probably using very traditional tools. Okay. RNNs have not yet become very good enough to actually do weather predictions as of now, as far as my knowledge goes. Okay. But let us come back to this picture here. Okay. So, let us say I make a simple prediction. I will erase this for a short while and then I will reintroduce this. So, let us say I have today's weather. This x here denotes, let us say, today's temperature. And this is my RNN structure. My RNN structure works this way. This here will predict, let us say, tomorrow's temperature. Now, x, just to be a little bit more realistic, apart from today's temperature, I give today's temperature, today's pressure distribution of various fields, let us say today's humidity, okay, and today's rainfall. Let us say all these are my inputs. Let us say I am taking 4 features. Okay. And tomorrow's temperature is my solo output. Okay. So, y hat is a scalar 1 cross 1, x hat or x is a vector which is 4 cross 1. Okay. So, let us say I have a neural network, this is that neural network, very simple neural network that is trained in the following way. You give today's temperature, pressure at a particular place or a particular height or something, humidity, rainfall, and then you predict tomorrow's temperature. This would be a 1-to-1 prediction, and that is just an ANN, it is not an RNN at all. Okay. But suppose we want to do this task. Not only do I want to predict Saturday, I also want to predict Sunday, okay, from just today's temperature and today's pressure, etc., mind you. Okay. So, we are not doing anything else. Now, can we exploit something that the interval between Friday and Saturday is the same as the interval between Saturday and Sunday? Okay. So, if I say that this output was some function of x, this output should be somewhat similar, okay, in its relationship to this output. Okay. Now, that is kind of encoded within an RNN. So, what do? You recognize that somehow the relationship here is similar to the relationship here, and from Saturday if I want from Sunday if I want Monday, that relationship is also similar, then again Monday to Tuesday, so on and so forth, which is what is being done. Of course, what will happen if you do this in practice is if you have a small error at some place, it will kind of propagate and it will grow, but this is the basic idea behind an RNN, which is you try to incorporate within the RNN the idea of equally spaced, repetitive temporal relationships, which is that you want the same relationship between H2 and H1 as is there between H3 and H2, as is there between H4 and H3, so on and so forth. Okay. So, this is a very simple idea. When I write it in a formula, you will see that maybe all this explanation was actually completely unnecessary. Okay. Now, before I go forth and all this explanation, even though you can keep it at the back of your mind for intuition, it is not necessary that deep learning researchers will agree with me that this is the basic intuition behind RNNs. Okay. This works very well for scientific and engineering problems. For language problems, it is actually quite amazing that it works, but that works because of the Turing complete property. Okay. So, please keep this at the back of your mind. I am just saying this for you to build your intuition, especially if you are from an engineering or science background. Okay. So, now that I have shown this picture, I have one H1 here, X1 here, and let us say Y1 hat here. I have H2 here. Remember, I have no corresponding X2. X2 would be the temperature and pressure and humidity and rainfall tomorrow, which I do not have, because I am asking for all this data today. So, I put the search on Friday and I want on Friday I want the result for Saturday, Sunday, Monday, Tuesday, Wednesday, etc. So, I cannot really get X back, okay, but X's information is somewhat encoded within H, okay, even though it is after a non-linearity, etc. It is encoded within H. So, I want to extract from that H, what could possibly be the temperature tomorrow. Similarly, I will reuse this H and try to predict the temperature day after tomorrow. So, how do we do this? Mathematically, sort of anticlimatically, mathematically it is very simple. Okay. Mathematically we will write it this way: in any box you have the following going on. You have HT, sometimes you have XT and sometimes you do not. You have HT minus 1 coming from the previous instant of time, and you will see later that sometimes you take out an output and sometimes you do not. Okay. Now, HT, as I wrote before, is a function. We will call this variously f, w, g, etc., function of HT minus 1 and xt. Okay. Now, what is the most general function we typically use within a neural network? It is very simple. We take linear combination followed by non-linearity, always that. Now, typically in RNNs we usually use tan H for the non-linearity in the hidden layers. Okay. So, in this case this will be tan H and we need a linear combination of H and X. So, there will be some weight matrix which will multiply H and some other weight matrix which will multiply X. Now, these two weight matrices in general will be different. Not only that, they will also have different sizes, as you will see very shortly. Now, this weight matrix we will call HH because it takes an H and gives out an H, and this weight matrix we will call XH because it takes an X and gives out H. Okay. So, this is the general formula for the hidden layer of an RNN. Some people will replace this tan H simply by FW or by G. Okay. Now, what about this YT hat? YT hat is equal to some function of HT. Now, in some cases it simply makes sense for this function to be a linear function. In some cases it makes sense for the function to be a non-linear function. Also, it depends on whether you are doing a regression task or a classification task. If it is a classification task and let us say it is a binary classification task, then G will become a sigmoid. If it is a multi-class classification task, you will use a softmax. Okay. And I will show you one example in the next video where we will have a fully connected layer with a full non-linearity followed by a softmax. So, all this can be, it can be linear, non-linear, depends on what you want to do. Okay. So, in something like the task that we have chosen, okay, we would probably make this into a simple if it is a single output, we will have like a sigmoid followed by a linear layer, something of that sort. Okay. So, let us do some further modifications on this basic example. So, the example I started with was I have X goes into H1, which depending on how far I want to predict in the future goes into H2, H3, etc. Let me erase this, I will come back to this later. Okay. And I take out temperatures. This is a classic one to many case. Okay. So, this is the case that we just saw. Let me put some numbers just for you to get a little bit of clarity. So, let us say x is 4 cross 1. Okay. We already know that y 1 is 1 cross 1, I am only predicting the temperature, x took more things. Okay. If you find pressure strange, you can look at wind speed or something of that sort. Okay. So, let us say we have some 4 features that we are taking in as input and we are predicting tomorrow's temperature, day after tomorrow's temperature, so on and so forth. Okay. How many? As many as we want. So, here itself you see the variation in sequential length. Not only can the input be of varied length, the output also can be of varied length, because you can predict forever, as against an ANN or a CNN, which will be able to predict accurately or not, its output size is also fixed. Okay. So, here in output size is variable. So, that is another property of RNNs. Okay. Now, let us see how input size can also be variable. Okay. So, let us say I made this prediction, I took today's temperature, wind speed, pressure, whatever, I gave some humidity and let us say precipitation. So, I took these 4, I predict today's tomorrow's temperature. Okay. Now, tomorrow came and I actually remeasured this data, took that day's temperature, I think I called it pressure, humidity and rainfall, and then I made this. Now, why can't I make simply this prediction? I would like to reuse this old data. Okay. So, yesterday's data also tells me something, today's data also tells me something. Okay. So, now instead of making this an independent ANN, I actually reincorporate this data by using this hidden layer input, and this would actually become a RNN. Now, I can use this and I will get slightly modified Y's now. So, now if I include this, this becomes a many to many prediction. Okay. So, many to many prediction could be I have maybe 2-3 days data and I predict 2-3 days data later. In fact, recently Google had a claim, actually they have not put up the full paper online as yet, that they have been able to predict an example of the RNN prediction would be wind farm usage prediction. So, this is fairly recent, about a week ago, which would make it around March 8 or 9 of this year they made this, and they were able to predict how much their load would go up or come down, and that would almost certainly be an RNN prediction. What would they use? So, they would use historical data of all the usage so far. So, you can see now you will have a variable size input. A variable size input would be as and when data keeps on coming, you can keep on adding this new data and your answers will change. Now, an example of this, in fact, a good example of this is when you start typing in some search term within Google, or nowadays even within Gmail, when you start typing something, as you change what you are typing, its prediction will change for what you are doing. Okay. In fact, even cell phones do that. I am not sure which of these use an RNN, but I am fairly certain that Google is using currently some version of some RNN sitting there with a combination of other traditional AI techniques. But that would be an example of a variable size input. As you give more, it gives you better or different predictions. You cannot do this with traditional ANNs or CNNs. Okay. So, an example of a many to many thing would be I give many days data and you give out future prediction of many days temperature. Okay. So, that would be many to many, and I would recommend that try looking at all classifications using this temperature example. And you will see that it fits in very well. Okay. You will see that you are able to find an analogy, and that is good for people from an engineering or science background, because we are not going to do, let us say, language tasks in this module, at least in this course. Okay. Now, before I end this video, I want to give you some idea of the numbers that will actually exist in this. So, let us take H2. H2 will be f of, or let us say tan h of WHH H1 plus WXH X2 plus, in general we should add a bias unit. Okay. I will talk about this in the next video. Now, you need to think about what is the size of this H. Okay. X was size 4 cross 1, Y was size 1 cross 1. What about the size of H? The size of H is like the size of any hidden layer of a neural network. This is arbitrary. Okay. So, you can give 100 neurons, you can give 200 neurons, how many ever you want. Obviously, you want to give a smaller number of neurons and make sure that your prediction is fairly good. Now, one question I am pretty certain will come, it could have come for you naturally even within ANNs or CNNs. What does H mean, or what does the data in H mean? Okay. So, we have a meaning for this, or we ascribed some meaning for X, which was temperature, let us say humidity, rainfall and pressure. Y was tomorrow's temperature. What does H mean? Actually, we do not know. So, what do? We simply always remember this, that this is simply the forward model. In the forward model, we simply postulate, we simply guess for a relationship between x and y hat, and this is the relationship that we are guessing. Okay. We guess this relationship and we just calculate what these w's are, that is all we do, and whatever those w's turn out to be, H has no further meaning other than that. As we have said a few times during the course, the meaning of this, trying to interpret this, is an open research problem. So, nobody knows this. So, why should this H go to this H? All we can say is somehow the information behind X is being stored in H and you want to reuse it. Okay. Since you do not explicitly know the pressure, humidity and rainfall, you sort of guess that somehow that information is hidden in H and I will reuse it. Okay. Now, one final very important point, which is what gives power to RNNs, is that this WHH and WXH and B, these things are constant with time. What does that mean? If I write down H3, H3 is tan H of WHH H2 plus WXH X3. You will notice that there is no X3, in which case this gets wiped out, plus B, the bias unit. Now, this WHH is the same as this WHH. So, you do not change weight matrices as you go forward. Okay. So, you do not change them at all, because that would mean a tremendous number of parameters for RNNs. The power of RNNs, or the reason why they are useful, is that you can use one WHH, one WXH and get done. Okay. So, that is what gives RNNs power. In the next video, we will be seeing a short example, a sort of a more detailed example than this one, the temperature one, and we will show it to you in MATLAB, and hopefully things will become a little bit clearer. You will also get a little bit clearer about what variable size sequential data means. Thank you.